not drive me nuts by making me wait forever to answer questions and stuff like that today. So, like my other classes have already. So, please. All right. So the remainder theorem. So the remainder, when dividing by x minus k, is the function value. So basically, what this means is like if you had a function f of x, equals blah 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 plus blah blah blah, minus blah blah. Like if we divide that function by x minus k, the remainder of that division is the value f of k. So by doing the synthetic division or the long division, if we want to do it that way, the remainder of that division will be the same as plugging k into the function and evaluating it. Okay? Which means that the ordered pair k comma f of k is a point on the graph, right? So remember when we plug in an x value, it spits out a y value, which we can then turn into a point on the graph. Okay? We're going to do this here in a second. It'll make more sense when we do it than when you just write about it like this. But okay, so this is the remainder theorem. It says that the remainder is the same thing as plugging, when dividing by k, is the same thing as plugging k into the function. Okay. Okay. I didn't have to create any new problems on this stuff, but I did have to go ahead and add some extra questions in. So you'll see those every once in a while. So like here on the next page, I've added these two questions into the notes. I should say p of x, not g of x. So we are going to just go ahead and divide p of x by x plus 1. We're going to figure out what point is on the graph of p of x, and then we're going to write p of x out in factored form, and then we're going to find all the zeros for p of x. Yep, so we're going to use synthetic division to do this. Okay. Remember the first step with synthetic division that you should always go through is check to see if there's any gaps. Okay, so just try to be really vigilant about that. You'll do it for a while. There won't be any gaps, won't be any gaps, won't be any gaps, and you'll get used to not being gaps, and then the next one will have a gap in it, and you'll get all screwed up. So just be really careful about that. Oops. So 1, 1, negative 5, negative 5. And then remember, when you divide, you're supposed to be dividing by the 0 of that. So yeah, that's why you set equal to 0 and then solve. That's why the sign flips. Okay, remember the easy thing usually is just to remember that the sign does flip. That's why the sign flips. You're supposed to divide by the 0 of the divisor, not just the divisor. So let's run through this real quick. Of course, bring down the 1. Negative 1 times 1 is negative 1. Negative 1 plus 1 is 0. Negative 1 times 0 is 0. Negative 5 plus 0 is negative 5. And negative 1 times negative 5 is positive 5. And add those, you get 0. So the remainder theorem says that the remainder will be the value of the function when we plug in what we divided out. So what that means is that p of negative 1, since we divided by negative 1, that means p of negative 1 equals 0. Whatever that number is there would have been our answer. So p of negative 1 is equal to 0. So that means the point on the graph is negative 1 comma 0. Right? Negative 1 is the value we plug in, the x value, right? 0 is the value that comes out, the y value, and so that point would be on the graph. Actually, we're going to do those two things there that I highlighted, but we're going to do them on the next section. So we can like kind of double check this to see if that's true just real quick if you want to, that p of -1 equals 0 just by straight up plugging it in. So -1 cubed plus -1 squared minus 5 times -1 minus 5. You know, -1 cubed is -1, and -1 squared is +1. -5 times -1 is +5, and minus 5. Of course, those give you 0, and those give you 0. So, you know, it does equal 0. They're just kind of saying that it does actually work. That it may seem kind of weird that we can divide something out and get the same thing as plugging something in, but it does actually work. So it's kind of cool. It does both those things. Sometimes you can hear synthetic division called synthetic evaluation. So because it does do both those things. So like I said, we're going to do those parts in the green and the yellow down here where the graph is. Just going to change my mind on that. The next theorem, the factor theorem, says that a polynomial p of x has a factor x minus k if and only if p of k equals 0. So again, it's kind of dense to read, but it's saying that the polynomial, so I guess, you know, kind of like this thing here, right? That the x minus k, that this is a factor of this. So is this a factor of this? Well, it is if, when we divide by k, our answer is 0. Okay, so we divided by k, k was -1, we got 0 as an answer. That means that this is a factor of this. Remember what this represents is the remainder. If the remainder is 0, that means the polynomial went in evenly. So that means it would be a factor. It's like dividing 35 by 5, right? You get no remainder because 5 is a factor of 35. Whereas if you divide 36 by 5, there would be a remainder because 5 is not a factor of 36. So, okay. So kind of restating this, if the remainder is 0, then x minus k is a factor of p of x. The point k comma 0, right? Any point that's number comma 0 is an x-intercept. All x-intercepts have y values of 0. So the point k comma 0 is an x-intercept of the graph p of x. Remember, the value that you plug in to get 0 as an answer is called a 0. So we plugged -1 in, we got the answer of 0. That means -1 is a 0. So that means k would be a 0 of p of x. It also means that x equals k is a solution of p of x. So I know in my Algebra 2 classes, I really pressed them on knowing that these three words and that one other phrase that we don't use very often, but root, that all four of those things really mean the same thing. Okay? They're very closely related. They don't mean the same thing, but they're very closely related. So that if you know the x-intercepts, that means you also know the zeros, you also know the solutions, you also know the roots. They're just written in different forms. That's really about it. But they're all about k, right? There's k, 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 right? Like it's not like that. So, right, but they're all just really closely related, right? Okay, so let's finish this up. So I want to write this function in factored form, and we're going to find the zeros, and that's going to help us do this graph. So basically what I want to do, I'll come back up here for a second, but I need this. So there was our remainder, right? And that means that was our constant. And think about, what you guys were doing the other day, rewriting these. Okay, so relabeling those and think about what this would be, right? So we have 1x squared, I have 0 x's, so I'm not going to write that. And then I have -5, and there's no remainder. So, that would come out as just x squared minus 5. Okay. I have 1x squared, no x's, and then -5, right? And there's no remainder. So what this is called is the resulting polynomial. So we divided p of x by x plus 1, and this is what's left over. So I'm going to bring that down here. In order to do this graph and think about these things that I asked you guys to do up here, I want to write p of x in factored form. I need to look at that resulting polynomial, and I need to ask myself a question. Can I factor this more? Can we factor that more? Let me try and go. No, why not, Maddie? It's not a difference of squares, okay? So Maddie's saying she's checking to see if it was a difference of squares. All right, it's got two terms. There's subtraction between them. First term is a perfect square. Oh, but 5 is not a perfect square. All right? Yeah, so there's no more factoring to do there. So that means that part of the function is done being factored. So far as writing p of x in factored form, I would use that x squared minus 5 and the original factor which we had, which was x minus 1, right? Now that's in factored form. Okay. Quick check to see if our answer makes sense at all. X squared times x cubed, right? Negative 5 times, nope, what did I do? I made that center. Oh, yeah, it's plus 1. Yeah, it was plus 1, not minus 1. So there I knew I was wrong because I got negative 5 and negative 1 give me positive 5, so I knew something was wrong. Yes, I had written that wrong. It should be plus 1. So I know the front and I know the back are right. Pretty good chance the middle's right. Yeah, but I don't need to check. At least my answer makes some sense. Yeah? And if I multiply those two things back together, I get back to where I started. And I can't break those two things down anymore. So that's factored form. The other thing we want to check, we getting zeros from there. Okay. What are the real zeros for this? So our zeros are, all right, we're just going to set that equal to 0, right, which we already did for this one. So we know one of the zeros is negative 1. We say x squared minus 5 equals 0, so we add 5 to both sides. How do we get rid of squares? Square root. What do we have to remember to do when we square root both sides? Plus minus, right, Rhea? I knew you would say that, right? Plus minus, right? That there's supposed to be two answers here, right? So this has two answers here and here. This has what other answer, right? This should have 3 zeros. So 2, 3. So here are zeros. Those are the values of x that make y 0. Okay? Well, why would I want the zeros? Why would the zeros help me graph? More specifically, so Grant's saying they're points, more specifically they're x-intercepts, right? If I want to graph something, then x-intercepts would be really nice to know. So let's turn those into x-intercepts. Okay, of course this one's negative 1, 0, that's easy. Now this one's going to be 2, so I'd have the square root of 5, 0, and then I'd also have negative square root of 5, 0. If I ask you guys to graph the square root of 5, is that going to be easy to do? No. So how do we need, what should the square root of 5 actually look like in order for us to find use out of it? Square root of 5 imaginary? And if it was imaginary, we couldn't graph it at all when those don't exist. So. I could say, hey, graph the square root of 9, right? But it'd be easier to say graph 3, right? I could say graph the square root of 5. What would be easier? 2.2-ish, right, Rhea? Right? What is the square root of 5? About 2.2, blah, 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 blah. Right? It's never ending. It's irrational. It's not imaginary. I don't know if you're getting confused there. That's just Minecraft. Square root of 5 is irrational. It's a never-ending decimal. It is a real number, though. So far as the graphing purposes, we do need to turn that into a decimal, or else we can't graph it easily. We don't know where the square root of 5 is, and this would be negative 2.2. So let's graph those 3 points. Okay. See, I had them there earlier and I forgot to erase them. So -1 and negative 2.2-ish and positive 2.2-ish. We can get one more point out of this graph, or out of that function really simply. We really don't have to do any work for it. We can find one more point really easily. There's a point up there somewhere. Yeah, what's the -5, Grant? It is our y-intercept, right on. So Grant says this is our y-intercept, so 0, -5. So we've got 4 points on this graph, right? This curve, it's gonna be a pretty crazy curve, okay? Definitely not enough to really tell us what the graph exactly looks like, but we also know a couple other things. Before that last quiz you guys took, I very briefly talked to you guys about end behavior. That was something that you guys had talked about in Algebra 2. I just kind of very briefly brought that back. And the idea was that by looking at that first term, its sign and its degree, so what the exponent is, so that's a positive and then it's an odd degree. That one ended up, any positive odd, the ends would look like the ends of an n. The middle would do could do all sorts of weird things, but the right end would point up and the left end would point down. So because the a positive number and it's an odd exponent, the ends will point like an N. So the right end goes up, the left end goes down. So if I try to sketch this, I can use that to be helpful. So from that left green point, if I just kind of slant down to the left, that way it's pointing down but slanting a little bit to the left. And that right green point, it's slanting up to the right because the right end's going to point up. Okay, that's what the end behavior tells us. So if we start on that left side and we just kind of follow along, right? It's not going to, as soon as I hit that that x-intercept, it's not going to like draw straight over, right? It's not a curve. That's not how curves work. Okay, so it's going to keep growing up, and it's going to eventually just turn around and come back down. What we don't know is like when that happens. We don't know where that turn is, but we know it's going to turn. What I can tell you guys right now is the closer those 2 points are together, the smaller that hump is. Okay, so those points are really close together, just barely over 1 unit away. So that hump is pretty darn short. Okay, it's going to keep going back down. It's going to go through that y-intercept. It is not going to turn. Yeah, I just know that. It's not going to turn at the y-intercept. It could, but it's not going to. Okay, so it's going to keep going down a little bit, and then it's going to turn, and it'll head back up. Okay, so there's kind of my sketch. I know the left end goes down. I know the right end goes up. In the middle, it's dipsy-doodling. Okay, but I don't know how far down it's going. I don't know how far up it's going. Okay, we might get there. I'm not sure if I want to go there with you guys, like talking about how to find those values and stuff like that, what they're called. I will just very briefly tell you that this is called a relative maximum. It's not the maximum of the graph because this graph goes up forever, but within this space, that's the highest point, so that's called a relative maximum. In the same way, this is called the relative minimum. Again, it's not the minimum of the graph because it goes down forever, but within this space here, that is the lowest point. Okay, so this is a relative max. This is a relative min. You can find those. It's kind of like finding a vertex, right? Just essentially, it looks like it's a vertex, but it's not the same. Okay, so here's what that graph would look something like that. I'll quickly show you that on Desmos just so you can see what's going on there. So there's the real graph. And you can see the x-intercepts. There's the negative 2.2 and the 2.2 that Ray brought up. There's the negative 1 that we had. Here's the y-intercept that Grant saw, the negative 5 down there. And we can see how the left lump is shorter because those two black dots are close together. Then if you look at the two right dots, how they're further apart, so that right moves down further. So because as further it goes sideways, it goes further down. And if it's close together, then it'll only go a little bit down. So, again, the amount that it goes down is pretty hard to figure out, but we do know it's just further compared to the other one. So, okay, you can see the ends point right in the way we thought they would. So, you guys won't be doing any graphing on your homework, just kind of trying to tie some of those ideas together, right? We're finding x-intercepts, we're finding y-intercept, we can find y-intercepts easily. So. Anything there? With the graph you guys want to talk about? Okay, cool. Saw the zeros in the exact form. Kind of already did that. What your WebAssign would want from you guys would be just a comma separated list. It doesn't ask for any special order or anything like that. So, we know that one of the zeros was negative 1. We know one of them was square root of 5. The other one was negative square root of 5. Right? Not square root of negative 5, but negative square root of 5. So those are the exact form. Okay. Remember the 2.2 was an approximation that we needed to help us graph. We can see 2.2. We can't see the square root of 5. It doesn't really make sense to us. We just don't think that way. Okay. So those are the exact zeros. Just a comma separated list is all WebAssign would want from you guys. If it asks you guys to write the product as linear factors, this is different than what we did earlier. So here's the factored form. X squared minus 5 times x plus 1 would give us that. It wants linear factors, right? Linear means it has an exponent of 1. So this is not a linear factor. Okay, that would be a problem. We couldn't type it like that. So all we need to do here is just give each one of these guys its own factor. We'll be good to go. So p of x would equal x plus 1. X minus the square root of 5, and then x plus the square root of 5. So those are the linear factors. So just going straight from the zeros to the factors, just switching that sign each time. So that would be how you would type linear factors or write out linear factors versus just factoring. Anything there? I put Grant to sleep. Oh, he's awake. He just looked really relaxed. You good, Colby? You doing okay out there, Tiger?
I think I got it.
Okay. Caleb, you hanging with me? All right. All right, last page. We're going to find out if negative 5 is a 0 of g of x. We can check that using another method, but we'll use the synthetic first. Then I want to go ahead and just practice writing it in factored form and finding zeros. The way the notes were laid out, it just didn't have a lot of practice doing the factoring, so I just wanted to keep throwing that at you guys. But you check to see if something is a 0 using the factors theorem. Okay. K is a 0 if the remainder is 0 when you plug it in or when you divide it out. Okay, so we're going to use synthetic division to check that. What's different here is that they are giving us a 0. They're not giving us a factor. So other than that, it's pretty much the same. Check for gaps, but there aren't any. 1, 1, negative 17, 15. So because they're giving us a 0, we use it as it is. And remember before they were giving us a factor, and I said, hey, remember you're supposed to find the 0 of this, that's what you divide out. Well, here they're giving us the 0. So we do not need to sign switch. Okay? They're giving us the thing we need, so we don't need to change it. Okay? So you just got to be careful about that. Let's run that through real quick. We got negative 5, adds to be negative 4, multiplies to be 20, adds to be 3, multiplies to be negative 15, adds to be 0. So they wanted us to check to see if it was a 0. Well, it gave us 0, so that means it is a 0. So negative 5 is a 0 of g of x. Okay. They said check using another method. So another method we could use would just be straight substitution. So let's just plug negative 5 into g of x, see what we get. So g of negative 5 would be negative 5 cubed plus negative 5 squared, and 17 times negative 5 plus 15. All right, so it's plugging negative 5 in. Negative 5 cubed is negative 125. 5 squared is 25. Negative 17 times negative 5 is positive. 10 is 50, 35, so positive 85, and plus 15. That would give us negative 100. That would give us a positive 100. So of course that's 0. So there again, just kind of confirming that using synthetic division will give us the same answer as using direct evaluation. So sometimes synthetic division is called synthetic evaluation. Just kind of depends on your goal here. So here this is more a synthetic evaluation problem because we're just evaluating what is that last number. As far as the question they're asking us, we only care about the last number, which is the 0. So it's more of an evaluating problem. I'm going to turn it into a division problem by the next thing that I ask you guys to do, which is let's go ahead and write it in factors. Okay. So if you're asked to write the problem in factored form, if they give you a 0 and say, hey, write it in factored form, now what matters is this stuff. Because that's where our resulting polynomial comes from. There's our c value, our constant. Here's our x squared, right? And this, of course, was our remainder. So that results in x squared minus 4x plus 3. Again, that's called the resulting polynomial. So you divide out what you know to get what's left. And just like before, we need to look at that and say, can we factor this more? So more factoring is the question we're asking ourselves right now. Can we do more with that? Last time the answer was no. Yes, Alasia, you say. What can we do with that, Alasia? AC? So what's our AC, Alasia? One times 3, okay, so AC is 3. And what do we need that 3 to also do for us? Add to negative 4. So Coley, what are our factors of 3 that add to be negative 4? Factors of 3 that add to be negative 4? Okay. So we got -3, -1. Those multiply to be 3 and add to be -4. Can we do shortcut or easy AC or the IM method here, whatever you call it? Or do we need to do full AC? Full? Elijah's saying we can do easy, Casey, we can do easy. Why can we do AZ, Katie? Why can we do a short one? You can always do the full. It's not wrong. It just takes longer. Yeah, A is 1. All right, A is 1, so that means we can go straight to the factors. X minus 3, X minus 1. And then that's only the factorization of that part, right? But we're done factoring now. There's no more factoring to do. Those two things, if we multiply them together, would not get us the original problem. Okay? To get the original problem, we need to bring this guy back. Just like we did on the last one. Right here. We had the x squared minus 5 and the original one that we divided out already. Right? So we got to do the same thing. We got to bring this one out. So for this time, they didn't give it to us as a factor. So as we bring that -5 down, we've got to turn it into a factor, which means it's going to be x plus 5. Okay? So here is g of x in factored form. Again, you can quickly check to see if your answer makes any sense. I have 1, 2, 3 x's. X cubed. 5 times -3 times -1 would be positive 15. Positive 15. Front and the back end match up. Pretty good chance the middle matches up. Okay? So, again, it tells you that your answer is not trash. It doesn't tell you you're right, but it tells you you're not trash. Not you trash. It's not trash. Okay? All right, so you can do a quick check just to make sure your answer makes sense. And then there's that, right? And finding zeros, that's easy, right? So find zeros. X equals -5. X equals 3. X equals 1. So there's our zeros. So it's really important that you guys are paying attention to what the problem's asking. Okay, it may ask you to just check to see if something is a 0 or not. Right? If all it wants to know is that, then we're done right there. Okay. It may ask you to see if something's a factor or not. If it said, "Hey, is x plus 5 a factor of this?" If so, it says like write the. It says something weird, but essentially what it wants you to do is type this in. It says basically wants you to write the thing that you would need to multiply it by, write the other factor that you would need to multiply it by in order to get the original. So it's saying like, does this divide into this? If so, write what you would need to multiply it by. It doesn't say it kind of like that. So you would write this. You would have been done there. If it says, find all the zeros, you would need to go all the way through this. So you really got to pay attention to the instructions. So I'm just giving you guys like multiple layers of these because there weren't enough factoring examples in here to kind of what I thought suit your guys' needs. So again, definitely all the problems won't be this intense. Some will be really easy. Determine if x minus 3 is a factor of p of x. You can check using another example. So again, I want you guys to pay attention here. It's giving you a factor this time. Not last time I gave you a 0, which is different. Okay. We're just going to use the synthetic division to check. So again, just check for gaps. Don't see any. And then we're going to divide that out, but we're going to divide out positive 3 because we're going to switch that sign. So 1, -11, 5, and 3. And then we are going to switch that sign as we bring it over since they gave us a factor. They didn't give us a 0. Okay. Watch out for that. Such a small difference, it'll completely change the problem. Of course, 3 times 1 is 3. -8 would be there. 3 times -8 is -24. That would give you -19. 3 times 19 is 57, so negative 57, negative 54. So is that a factor? It's only a factor if that was 0. Okay, so x minus 3 is not a factor of p of x. I believe how the computer wants you guys to address that is if it doesn't work, is they want you to type in the phrase does not exist, so just DNE. Because again, the way they ask is if it's a factor, type in the what you would need to multiply it by in order to get the original thing. Well, what that means is there's nothing you can multiply x minus 3 by to get this. So that thing that you would multiply this by to get this does not exist, is what they're trying to go for. Okay. Again, the other way to say that is, what would I need to multiply x plus 5 by in order to get this? They would want you to say this there. You wouldn't need to do the rest of it. Okay, you could stop right there. So you really got to be careful about the question they're asking you. Okay? Is this a factor of that? If so, write the factor you would need to multiply by. That's all you would type. If we wanted to check that, right, check to see that it doesn't work. So one way we could check that is to, knowing that this is a factor means that that's a 0, which means it's also an x-intercept. We could look at the graph and see if it has an x-intercept of 3. If it does, then that means we screwed up something. If it doesn't, then that means we were right in what we said. So we look at the graph of this real quick. Luckily, I have that prepared. Okay, so here's the graph of that function. You can see the x-intercepts are definitely not. Neither one of them is 3. So there's the other one, actually. There it is. So there's the x-intercepts, right? None of them are 3, so we were right. Okay. Anything on question 4 you guys want to talk about? Okay. All right. Last one's really pretty much the same thing we've been doing. They're giving us a 0 or giving us a factor. They want us to factor it. And then I just threw on there and find the zeros because just to kind of finish it up. But so really no different than what we've been doing. So they're telling us that this is a factor. They're not asking us to check. They're saying it is one, which means that this will work. Okay. Check for gaps. There are no gaps. So we got a 2, a 5, a -1, and -6. Because that's x minus 1, we're going to bring over +1. So we're doing our sign switch. Drop the 2, run through that. 1 times 2 is 2, plus 5 is 7, times 1 is 7, plus -1 is 6, times 1 is 6, plus -6 is 0, right? So again, that 0 basically is just a good thumbs up because it's just confirming that this was true, right? That is a factor. It's not telling us anything else right now. We already knew it was a factor. It's just letting us know things are going well, okay? We're here for this. The reason we did all this was for these guys, right? That's our remainder, that's our constant, that's our x, that's our x squared, right? That's what we're here for. So we're going to bring that 2x squared plus 7x plus 6 down. And what are we going to ask ourselves now? Once we have that resulting polynomial, what's the question we ask ourselves? Yeah, can we factor, right? So more factoring, right? Question mark. Can we do more? So what do you think about that, Grant? Can we factor that? Yeah, how are we going to do that? AC, so what's our AC? 12, and we need 12 to do what? Add to 7. So 3 and 4, right? So Grant, so can we do the shortcut here or no?
I don't know how to do the shortcut.
Grant does the long way every time. So Katie, and when can we do shortcut? I guess they're right up there still. So if A is 1, we can do the shortcut, right? And then A is not 1, so no shortcut, right? No shortcut. So we got 2x squared plus 3x plus 4x plus 6. Group it, so those both have an x. Those both have a 2. All right, here's the next little thumbs up, right? The 2x plus 3s are the same, so that means everything's going well. So we've gotten 2 kind of built-in checks into this process. That first 0 that we got lets you know things are going well. The 2x plus 3s let you know things are going well. It says factor this completely, right? We're done factoring that. So the only thing we'd have left to do here would be to slam that x minus 1 back onto the front or the end. It doesn't really matter. And then r of x would equal that. There is the factored form of that original polynomial. Again, quick checks. X times 2x times x would be 2x cubed. Bada bing. Negative 1 times 3 times 2 is negative 6. Bada boom. Okay? Front works, back works. Pretty good chance the middle works. Okay? Then I asked you guys to find the zeros, which is super duper easy. So if x minus 1 equals 0, of course, x would equal 1. 2x plus 3 equals 0. Subtract the 3 over, divide by 2. So x equals negative 3 over 2. X plus 2 equals 0. So, of course, x equals negative 2. So there's our zeros as well. Right? Finding zeros is easy once you got it factored. Remember, we do have like a short day tomorrow, so our work period, isn't the full 50 minutes or whatever. So it would definitely be helpful if you guys come to class with there's only 7 problems at any time anyways, so it's pretty short. But it's be helpful if you can come in with some of it done. That way you're just asking the questions you need help with, and but I don't know that any of you leopards are changing your spots at this point. You're coming